Hello friends, welcome to this video. So in the last video I was actually talking a little bit about something called pseudo-random binary signals, PRBS. Okay, so PRBS. And what's the advantage of pseudo-random binary signals? Okay, so the thing is that, like noise, you can actually test a number of frequencies at one go. Okay, so the main thing is that you can always test more than one frequency at one go, and of course people actually use it to test the systems as well. It's been commonly used before, so they don't use just the background noise but a pseudo-random noise. Why is it called pseudo-random? Okay, so the reason why is because we don't actually use a so-called a true random number generator, but instead there's the algorithm behind the pseudo-random number generator. I mean, there is a fixed algorithm. Okay, I won't be going into that in detail, but I will just say that for frequency response testing in LabView, you want a time-varying pseudo-random binary sequence output. Okay, so if you really want a pseudo-random binary sequence output to test over various frequencies, now this is how you do it. Okay, so LabView does not have a pseudo-random signal generator in the control design and simulation. There are only like step signals, pulse signals, ramp signals. And the signal generator we have explored, it does not have the pseudo-random thing. It has a random wave generator, but it's not like anything we want. It doesn't give us the degree of control, so we have to like customize things. What kind of degree of control am I talking about? Okay, so for random noise, we have a signal going up and down like that. Now to replicate this signal in your system may not always be possible, so the kind of noise you would want is probably something a bit slower. So I like to call it like a slow noise, because for example, I want it to be at a 0 value for at least 7 seconds, and maybe I shift it to a 1 value. So the high value is like a 1, the low value is like a 0. So that's why we call it binary. So you'll be staying for 7 seconds at least. Okay, so how do we get this started? So that's the question we're trying to solve in today's video. Okay, so anyway, we don't have it natively with LabView for signal generation in the control design and simulation. The closest thing we have is in the waveform. Okay, under waveform, you go to analog waveform, you go to generation here, and you will find a lot of waveforms. For example, a basic function generator, that's one. You have tones and noise, a formula function, a sine waveform, a square, triangle. All of this we have it inside our signal generator. We also have multi-tone. Okay, multi-tone meaning to say you can have a start frequency, a change in frequency. Okay, so you for this one you have a start frequency, maybe F0, then you go to F1, okay, F2, then you have a delta frequency here which you can manually set, and then this multi-tone generator will give you the summation of the output. Okay, it will give you the actual tone frequencies and of course a waveform. Okay, so this is what the multi-tone thing does. You can specify how many tones you want, all that stuff. So but it will not give you a time varying output. It will give you a waveform, which is this brown color dotted line thing, and somehow you need to convert that into a time varying input. Okay, so that's not I mean, I'm pretty sure there's a way to do it, but I just haven't figured out a way that doesn't take so much effort. I don't want to put in that much effort, okay, honestly. So it's just we want to be efficient, maximum results for minimum effort. Okay, But anyway, these are your multi-tone generators that you can do a summation of sine waves. Okay, and they seem to be only sine waves. Okay, there's a uniform waveform. They call it uniform white noise waveform.vi. There's a Gaussian white noise, which again is like you kind of filter some frequencies off. There's a periodic random noise waveform. Okay, periodic random noise, which I'm not going into. Inverse F noise waveform, inverse frequency waveform, so it's like a low pass filter. Gamma noise waveform, Poisson noise waveform, binomial waveform, and blah blah blah. Okay, so what we are looking for is this thing called MLS. Okay, MLS actually stands for maximum length sequence. Okay, MLS. Okay, so yeah. I'll open Chrome. Okay, hello, Chromium. Yes, okay, took a while. Okay, so Chromium, which is basically the open source version of Chrome. So yeah, let's do MLS, maximum length sequence, and this is what this is about, maximum length sequences. Okay. Okay, so this is one sort of a pseudo-random binary sequence. Okay, is a subclass. We are talking about pseudo-random binary sequence. This is the Wikipedia page for it. What LabView has is this thing called an LS. Okay, it's a string of so-called they try to it's a string of zeros and ones. So it's a random looking string of zeros and ones. Okay, a random looking string of zeros and ones. All right, and what you do is that every x number of bits, every n numbers, right? So this is one number, two number, three number. We like to call these numbers bits. Okay, we like to call these numbers bits. So this 1 bit, 2 bit, 3 bit, blah blah blah. So if we have a 32-bit sequence, a 32 number long sequence, we call it 32-bit sequence. Okay, 32-bit sequence. If not, we have 64-bit sequence, 1, 2, 8, 2, 5, 6. Usually they go in powers of 2. So 32 times 2, 64, 64 times 2, 1, 2, 8. So that's usually how things go. So if we have an n-bit sequence, okay, so within this sequence itself, it looks random. But let's say after your 32 bits are up, and if you have a 32-bit sequence and the 32 bits are up, they'll do this, they'll keep repeating the sequence, yeah? Okay, because after you reach your maximum length, or let's say if you specify 32 bits, then the sequence will repeat, zeros, ones, zeros, ones. Okay, and basically that's what's happening. Okay, this thing in LabView. Now, in this MLS sequence, okay, let's show you how it's so-called done. Okay, the way to do it, well, I'll probably have to, yeah, usually I can use a new VI, and then I'll just show you one time how it's done. So you go to waveform, go to analog waveform, go to generation, go to MLS, and this is the pseudo-random binary sequence. Okay, you don't really need to put anything in, but what I will do is just give you a waveform chart. So I can create indicator. There's a signal out, okay. It will show you this number of things, and I can also show you a waveform chart. Okay, waveform chart. Now just wire this in, and I'll not save this, but let's play this and see what happened. Okay, so it will give you a sequence of so-called zeros and ones. Okay, it will give you a sequence of zeros and ones. If I actually pull this down, okay, you'll see a very long sequence of just zeros and ones. And this is what the MLS sequence does for you. It will just give you a semi-random looking series of zeros and ones. And every time you press play, the sequence will change. Okay, so this sequence of zeros and ones will change. That's the only thing the MLS thing does for you. Not the best, but you know, we work with what we have. So the idea is to quickly, you know, convert this this into an array of sorts somehow. Okay, we have to convert all this into an array. Okay, so we can do something called get waveform. Yeah. Waveform components. Okay, so if I get this waveform, I will get the waveform components like that, and I will create some indicator here. So if you want to get an array from the waveform, you go to waveform and you get waveform components, this first thing on the top left. And this thing will be blue instead of orange because it is giving you integer values. Okay, it's giving you integer values. Alright, so when you press play, your array of zeros and ones will be nicely displayed here. And every time you press this play button, the array will be randomly rearranged, so to speak. I mean, for all intents and purposes, it looks random. That's simple enough. Okay, so okay, the thing is that, you know, how do you know how many bits this thing is? How many what's the length of the sequence? So what you usually do is one thing, of course, you can take a look at the documentation, MLS labview, maximal length sequence, binary MLS VI. Okay, so this is what you would usually get. Is it the same one? Oh, not quite. Okay, but more or less it's there. Okay, so it's okay, go to analog waveform, go to generation. Okay, this is where you get your MLS stuff. What you are seeing now, okay, if you look at the block diagram of this thing, it will have this thing called binary MLS. Okay, binary MLS. Okay, this is very important, and this is the VI we sort of want to use as well. Okay, so go to you can go and search for binary MLS. Okay, so where is it? Okay, this will be under mathematics, under signal processing, signal generation. So go to signal processing over here under mathematics, and you go for signal generation. Okay, signal generation. Then you have all these things here. Again, you have MLS, you have all the noise which you can generate. Okay, so binary MLS will be here. So instead of getting a waveform, which you have to convert every time, you will just get your array. So these are two ways of getting your MLS sequence, maximal length. Okay, so I can just make an indicator here. And again, I will just press play. Every time it will show us a different set of random numbers. Okay, so what can you control here? You can control the number of samples. By default, it is 128. So I said that, you know, you have samples in orders of the normal number of samples for this MLS sequence is usually in multiples of 2. Okay, I won't explain why, but yeah, just take it as it is for now. So if I put a sequence of 8 numbers, okay, if I put a sequence of 8 numbers, I expect to get a sequence of 8 numbers. So there are 4 ones and 4 zeros. Okay, 4 ones and 4 zeros. Okay, so most of the time they will try to make sure that, you know, your numbers of ones will equal to the number of zeros. In some cases, when you have very short sequences, okay, the number of zeros can be more than the number of ones and vice versa. So that's why you, more often than not, you want to use a longer sequence, maybe like 128. Then you press play, and given the law of large numbers, you will have roughly equal number of ones and zeros as you increase your sample size. So I recommend going for samples of 30 and bigger. or 50 and bigger, if not 100 and bigger. Those are what you want to get. Okay, so the next thing is there's this thing called polynomial order, which over here, according to this what do you call that, documentation, it specifies the order of the modulo 2 primitive polynomial used to generate the MLS sequence. Okay, so this thing is something I do not touch. Okay, we just want a random sequence of numbers. Whatever mathematics that goes behind doesn't really concern me at the moment. So we just want a random noise-like signal, which we can adjust how long the signal stays at 1 or 0. Okay, so these two, polynomial order and seed, is maybe for more advanced users of it. The thing you kind of want to control here, at least that makes the most sense now, would be the number of samples. Okay, default number of samples or number of bits, we like to call it, is 128. Okay, so what it gives you again is this sequence of zeros and ones, which is, well, half the problem solved. It is not the full problem solved because you need the zeros and ones to actually alternate with time. Okay, your zeros and ones should alternate with time, so that if you have a chart here, okay, our well, I have 428 samples, which is the bit length. So I already made this VR subsystem. Okay, it should actually alternate between 0 and 1. So now it's maybe there's a very long string of zeros. Okay, that's why this thing is like this. Okay, or long string of ones for that matter. Yeah, so you can see this. This is how the so-called slow white noise will look like. The slow sequence of white noises. Yeah, so if you can for this I can actually adjust how quickly the ones and zeros change, like this. So the question is, how do you get from the array into this time varying signal, which you can then plot out and use as your input? Yeah, so that's the challenge of the VI that we are trying to do here. Okay. So these are all the, again, ones and zeros that we are putting out over time. Roughly, you need the number of ones and number of zeros to be equal. Okay, so that's what we want to have. Okay, so how are we supposed to do this? Okay, so let's take a look at this subsystem. Okay, and okay, before I go, of course, yeah, you gotta think. Okay, you gotta think. Okay, once you generate a series of ones and zeros, how then do you cycle through these ones and zeros? Okay, let's say time equals 0. I want my pseudo-random generator to put out a number of 0, and this one is maybe at time equals to 5 or time equals to 7. Then okay, I'm going to put out another number, time equals to 14. Okay, time equals to 14 seconds, and then I put out the third number. And then once I go to the last number here, I will need to cycle back to the first number after the appropriate amount of time. Okay, so how do we do it? Okay, so we actually have to cycle through this. Okay, so let me explain how I did it. Okay, so I have this bit generator. Okay, so I have something that actually generates the pseudo-random sequence. Okay, and the only instead of running it at every okay, let's slow down a while. This pseudo-random under signal processing, you go to waveform, not waveform, signal generation. You'll see this thing called binary MLS. Okay, your MLS sequence will change every time you hit the run button. Okay, your maximum length sequence will change every time you hit the run button. So that's not exactly what you want. Okay? It's not exactly what you want. You just want to generate the string of ones and zeros only one time. Okay, when you start the play button, you only want to start it one time, and then after that, you don't want it to you don't want to change anything. You just want the sequencer to kind of repeat itself. Okay, you want to use the sequence you generated at the first time step. Now, how do you get this done? Okay, so there's a number of things you need to pay attention to. Okay, first thing is that yeah. Again, we want to have a structure such that we only generate the pseudo-random sequence the first time we run the loop. Okay, the first time we run the loop. Okay, so how do we check whether the loop is being run the first time? Okay, so we have this thing called a, well, it's basically something to check if the loop is being run the first time. Okay, and it's this little function over here, which let's see. Okay, I can't exactly remember the moment. Okay, so the thing here, it's called a first call. So if you can't remember, just right click, go to properties, and you will find the name of this label. They call it a first call. So you go to functions, you go and search, you go and put first call. Okay, first call. So this first call will be under data communication synchronization. Okay, so let's go right click, under data communication, you have synchronization, you have this thing called first call. Okay, this is your first call. So first call. Okay, what does the first call do? First call basically checks whether, are you running the loop the first time, or are you running the loop not the first time. Okay, so this, if you're running the loop the first time, this first call thing will return a 1, otherwise it returns a 0. So it's a true or false value. So if you're running the loop the first time, I want my MLS sequence to generate the thing. Okay, so based on the bit length, how many bits does this sequence have? I explained the concept of bit just now. Okay, how many bits does this sequence have? Okay, so if it's let's say your default is 128, so we have 128 samples. You pump that into the generator here, MLS generator. Okay, maximum length sequence generator, and that will give you the first MLS sequence. Okay, however, what happens if it's not the first call anymore? It's not the first time you're running the loop iteration. Okay, you kind of want to use the same MLS sequence. You want to use the same sequence of ones and zeros. So instead, this thing will be false. If it's not the first call, we will have it false. So we will not be generating new MLS sequences, but we will keep using the same sequence we had before. So I use this thing called memory. I use this thing called memory here. Okay, so what memory does is that it takes the MLS sequence from the last iteration, it stores that value, and then it will so-called save it for your next iteration. So okay, so what does it mean? Okay, the first loop, you generate the MLS sequence. The subsequent loops, it is stored in this memory, and then let's say loop number 2, it will recall the MLS sequence from loop number 1, and then you'll pass it into this this case structure. Okay, and then you will the code will ask, okay, what's your MLS sequence at loop number 2, at time number 2, or your second iteration? Then because we wired it this way, your memory will actually pass the MLS sequence, the pseudo-random sequence, from the first iteration back into the loop, and it will, and basically you're telling the code. You're telling the code, okay, at at the second iteration, I want my MLS sequence to be the same MLS sequence, the pseudo-random sequence. I want it to be the same pseudo-random sequence as what I had in the first iteration. So that's why I'm having this memory loop thing here. It's not the most efficient way of coding, but it's something that makes intuitive sense to me. Of course, we can update this code to be computationally cheaper, not a problem. But this is how I would do it now. Okay, so at every time you run the code, the pseudo-random generator will check whether is this a first call, okay, and then it will give you the idea. I'm trying to it will give you the thing. Okay, what am I saying here? So okay, basically you only generate your binary sequence the first time, and every time after that it will just use the same sequence that you generated at your first time step. Okay, now once you have this sequence, how are you going to get numbers out of it? Okay, I want a time varying value of ones and zeros. Okay, so I use this thing called index array. Okay, index array, because the first thing you'll be putting out is the array, and to index the array. Okay, so let me run this thing once. Okay, that's not going to work. 1, 2, 8. Okay, so I have what do you call that? I have a long string of ones and zeros over here. Okay, and if I run continuously, I'll have these strings of ones and zeros continuously changing. Okay, so if you want to index the array, if I want the first element, okay, I start from 0. Okay, if I want the first element, then you start from element number 0, and then you can check the MLS output. Okay, so basically what are we expecting here? Okay, let's say we want element number 3. So we will take index number 2 because we start from 0. So we press play. Okay, so I look at the index number 2. So this is index number 0, index number 1, index number 2. Okay, and the number here is 1. So I just want this number 1 to be here, and this will be the number 1. Okay, so I'm looking for the index number 2, the number in the index number 2. So the way you sequence arrays or something, index arrays, you have to supply the index number. So this is 0, this is 1, this is 2, and what the labview will do is that it will give you the value at that number. In this case it's 1. So I can press play another time. Okay, again this is a different sequence of numbers. This is index number 0, 1, and 2, and again the number at 0 at index number 2 here is 1. I can keep playing until the index number at 2 turns to 0, and then you look at this time. This time the index number at number 2 is 0, and then the MLS output is 0. Okay, so to get the correct number which I want from my sequence, I will just use this index array. Okay, so this is one part of the code that will say, okay, I only want to generate the maximum length sequence one time, and every time after that I will only read that same array. Okay, I will get values of that array using this array indexing thing. Okay, so that's the first basic part of how it works, and I'm going to stop now, and I'm going to continue next time. Okay, bye bye.